Okay, so just to wrap up this discussion of MapReduce versus databases, I want to go over some results from a paper in 2009 that's on the reading list where they directly compared Hadoop and a couple of different databases and see if we can maybe explain what some of these results tell us. Okay, so this was Andy Pavlo and some other folks at MIT and Brown who did an experiment with this kind of a setup. So the comparison was between three systems: Hadoop, Vertica, which was a column-oriented database, and DBMS X, which shall remain unnamed, although you might be able to figure it out. And so we haven't learned what a column-oriented database is and what a row-oriented database is, but we may have a guest lecture later that will describe that in more detail. But for right now, for the purposes, just think of these as two different kinds of relational database, or two different relational databases with different techniques under the hoods, under the hood. Okay, and so there's two different facets to the analysis. One was sort of qualitative about their discussion around the programming model and the ease of setup and so on, and the other was quantitative, which was performance experiments for particular types of queries. Okay, so the first task they considered was what they call a grep task, and so this is a task to find a 3-byte pattern in a 100-byte record, and the data set was a very, very large set of 100-byte records. Okay, so this was done this task was performed in the original MapReduce paper in 2004, which makes it a good candidate for a benchmark. And so the data set here is 10 billion records with totaling 1 terabyte spread across either 25, 50, or 100 nodes. Okay, so you're just trying to find this record. So this is much like this genetic sequence DNA search task that we described as a motivating example for sort of describing scalability. Okay, fine. So what were the results? Just to load this data in, this is what the story sort of looked like. Hadoop and the system called Vertica, that they're really the theme here is they were the designers of the Vertica system. And so most of these results are going to show Vertica doing quite well for a variety of reasons. So we're not going to talk too much about those particular reasons. We're mostly going to be thinking about DBMS X, which is a conventional relational database, and Hadoop. Okay. So here, loading is fast on Hadoop, while loading is slow on the relational database. And again, it was sort of fast on Vertica as well. So why is it faster on Hadoop? Well, there's not much to the loading, right? You have to put it into this HDFS system, so it needs to be partitioned, but that's about it. When you put things into a database, it's actually recasting the data from its raw form into internal structures in the database, and that takes time. Okay. And the process could be even worse, because if you're building indexes over the data, you actually, every time you insert data into the index, it needs to sort of maintain that data structure. Okay, and so load times are known to be bad. So the takeaway here is, remember that load times are typically bad in relational databases relative to Hadoop because it has to do more work. Now, once it's in the database, you actually get some benefit from that, and we'll see that in a second, even in these results. But it's actually, we know that it conforms to a schema, for example. Hadoop is just a pile of bits. We don't know anything until we actually run a MapReduce task on it. Okay. And so how much faster? Well, in their experiments on 25 machines, we're up here at 25,000. These are all seconds, by the way. 7,500 seconds versus 25,000, and a little bit less as we go up to more servers. Okay. Now, actually running the grep task to find things, this is what we see. Again, maybe ignoring Vertica for now, because I haven't explained to you what the difference about Vertica is that allows it to be so fast. But just think about a relational database from what we do understand. Hadoop is slower here, and the primary reason is that it doesn't have access to a index to search. So again, no index is available. Hadoop has to do a... That's wrong. Okay, so Hadoop is slower than the database, even though both are doing a full scan of the data. The grep task here is not something amenable to any sort of indexing. You actually have to touch every record, so there's no fundamental reason why the database should be slower or faster. But partially because it gets a win out of the structured internal representation of the data and doesn't have to reparse the raw data from disk like Hadoop does. And so I said there's no fundamental reason. There is a fundamental reason, because it's already in a kind of a packed internal binary representation, which we paid for in the loading phase, but now we get the benefit from here in the query phase, even before we even talk about indexes. Okay. Now, a selection task where you're not having to scan every record necessarily, that is amenable to indexing, as we discussed in the scalability segment. Well, the story is even more extreme, right? The Hadoop results are just way, way, way higher than both the database and in particular the Vertica results. And so here, the reason is because you can build an index on the PageRank attribute and zoom in directly to the records that you're interested in. Okay. Fine. So those are sort of search and retrieval tasks, arguably not exactly what Hadoop was designed for. Hadoop was designed more for analytical tasks. So now consider these. So here the data set is 600,000 HTML documents, which works out to be about 6 gigabytes of data per node. Along with another data set is 155 million user visit records and 18 million rankings records. So this is kind of a web data processing task. All right. And so a simple aggregate task here is to add up all the ad revenue corresponding to a particular subdomain. So they apply this function substring to the source IP to pull out the first 6 characters, right? The subnet mask of the first prefix of the IP address. Group by that, and just add up the ad revenue. Okay, so this is one thing to point out is it's actually very nicely and simply expressed as a SQL query. You don't necessarily have to write a bunch of Java code and MapReduce to express it in this particular case. Okay, and so here are the results. Again, you see a row-oriented database beating Hadoop, and the reason here is maybe not quite so easy to explain, but essentially it's the internal representation in the database again wins credit. There's no parsing that has to happen. Okay. Okay. On this same schema, there's a join task, which is to find the source IP that generated the most ad revenue along with its average page rank. And so this is kind of a complicated thing involving multiple passes over the data, to sort of compute the average page rank and then find the source IP that, find the maximum ad revenue, find that corresponding source IP, and then compute its average page rank. And so the implementations here are a fairly complex SQL statement involving the use of temporary tables. And in MapReduce, it has to be 3 separate MapReduce jobs chained together. Okay. And so for the complicated SQL, we won't go through this in too much detail, but just notice that there's a join, and then there's a group by. We looked at some complicated SQL, and we sort of showed how to break them down, and this is no different. So there's you see 2 tables, which you should think to yourself join, and then you see a group by, and so those are really the 2 tasks going on. And then the second step is to do a big sort, because you see the order by and just find the topmost record. Okay. Fine. A join and a group by. And so here the results are also pretty impressive. And the reason is, again, because of the indexing, right? this join can be done very, very quickly because there's different kinds of ways to do the join. The one we described for MapReduce is when you have no information about the schema. All you've got are these two big relations, and you have to scan them both in parallel and shuffle them across the network with respect to the join key, and then perform the join. But if one of them is indexed on that join attribute, you have other plans available to you, and the database is automatically going to figure out the right one thanks to the magic of relational algebra. And so that's what's going on here. And so both Vertica and the relational database can do a lot better. Okay. Now, so that's fine. So that sort of paints the picture that maybe relational databases are great, and boy, this MapReduce framework is all wet, and why would anyone use it? Well, we talked about fault tolerance, but a couple of other things. There's other ways to avoid sequential scans that you can actually implement directly in Hadoop. So for example, if you have a large relation and a small relation, one thing you can, and the relation is small in the sense that it fits on a single node. It doesn't need to be partitioned anymore, which happens a fair amount. You could actually broadcast that, make a copy of it, and send it to every machine in the cluster, or at least every machine that has a copy of the other relation you're joining against. Right? So you're joining R and S is small and R is big. We'll just copy S to every partition of R, and now you can do the join locally without having to do this sort of shuffle phase. Okay. And so they didn't get a chance to take advantage of that mechanism. Moreover, there are, especially in modern systems, this paper was in 2009, which is now a little bit old, or quite a bit old, there are ways to provide indexing capabilities in a Hadoop stack. And so you're not sort of dead in the water when you aren't allowed to use indexing. So the positive view, if you look sort of warmly on this work, you can think, great, relational databases have all these benefits, and Hadoop can't really compete on some of these very basic queries. Another way of looking at this is, well, these tricks that we already know work really well, like indexing, do indeed work. And so all we got to do is add those to Hadoop, and we'll get the same kind of benefits. Okay. So what's interesting here is to read about the response from Google when this paper came out, which was a discussion published in CACM. And one of their points was that the largest known database installations were both at eBay at the time, which was a Greenplum on about 100 nodes, and a Teradata system on also about 100 nodes. And the largest MapReduce installations at the time were way larger, right? Nearly 4,000 at Yahoo and 600 plus at Facebook. And again, this is years ago. So these numbers are much higher actually in both cases, but I think the overall point is still the same. The size of even perhaps typical Hadoop cluster is pretty enormous. Okay. To conclude the comparisons, we've said this a couple of times, but just to wrap it up one more time, what can MapReduce learn from databases? In the words of the authors of this paper, is that declarative languages are a good thing, schemas are important, and what can databases learn from MapReduce is this query level fault tolerance, support for what I'm calling is in situ data, which is data as it lies, right? Supporting don't require that the data be sort of transformed and loaded before you can work with it. And then maybe embrace open source, because if there had been an open source parallel database available, you might not see the same popularity in MapReduce. Okay. Other systems that have been considered in the same kind of framework after the fact were HadoopDB, which became Hadapt, which I mentioned, is now a startup. And this is Hadoop file system, but has it's actually not Postgres anymore. It's MonadDB. But the point being, a relational database on individual nodes in order to get some of the indexing and some of the at least local level benefits of relational query optimization. And then Hive also came out since then. Fine. So that's the end of MapReduce of both MapReduce itself and MapReduce compared to relational databases. And in the next segment, we'll talk about NoSQL systems that are solving a slightly different problem.